Welcome back to the video lecture series for Introduction to Additive Programming using Scala. In this video we begin a new chapter, and we're talking about the concept of trees. Now of course a tree is something that everyone is familiar with. A tree. Of course normally when you hear the term tree you think of the biological trees, things that grow outside and they have leaves and they're green because they have chlorophyll in them, and that causes them to do photosynthesis and convert sunlight into energy. We're not going to talk about those trees. We're talking about the tree as a concept in computer science. And so I want to start off by giving kind of a definition of what trees are like, and then we'll go looking at how we can program trees inside of Scala. So in the videos for the previous chapter we talked briefly about graphs, and we said that graphs were made out of vertices and edges. Well, it turns out so are trees. So here we have a vertex. We'll go with two vertices here, and if we create a tree, we need some edges in between them. Let's go with this type of connector here. Okay. So here we have one vertex and another vertex, and we have an edge between them. Now, of course, in the case of graphs, we can do whatever we want here. And it was mentioned that in some ways a linked list is just a graph where every vertex has an edge that links it to one other after it. A tree doesn't have the same flexibility as a graph, but it does have, so it has some rules, but it's not quite as limited as a linked list. So what are the rules for a tree? Well, once again, our edges connect vertices, and the rules for something to be a tree. Your graph is a tree if and only if every vertex has exactly one incoming edge, edge into it, with the exception of one special one, and this one special one is the root. So the one vertex that has no edges coming into it is the root, so it has 0 incoming edges, and everything else has 1. Now note that this allows us to do something that we couldn't do with our linked list. So while that right there is a valid linked list and a valid tree, this is still a valid tree. Okay? Every one of these vertices has one incoming edge, except for the root, which has 0. And so the thing about trees is that they have this branching structure to them, hence part of the terminology why we call them trees. They don't have to branch, of course. It turns out that a linked list also satisfies the definition of a tree. So if I were to draw out a linked list, you'd notice that there would be one vertex that has 0 incoming edges, and all of the others have exactly one incoming edge. So a linked list is actually a valid tree. Now, some things that fall out of this. Because everything has one incoming edge and the root has 0, it turns out there is exactly one path from the root to any other vertex. So wherever we want to, whatever we draw for our tree, no matter how many edges come out of them, turns out that pick any one of these and there is exactly one way to get from the root to there. Okay? You can't have cycles and you can't have loops. So if I do something like that, this is no longer a tree because now I have a vertex that has 2 incoming edges, and now I would have these 2 paths to get there. You can also think of a tree in using a recursive definition, whereas a tree is either empty or it is a root with 0 or more subtrees underneath it. Okay, so we're defining a tree in terms of a tree there. We call these vertices or nodes. When I write code, I'll call them nodes. I find it easier to type than vertex. When we talk about trees, we kind of use some mixed metaphors here. We're going to mix the biological terminology Obviously, we have some biological terminology here. We have root, which is the name that we use for the one vertex that has no incoming edges. Something to note that computer scientists draw their trees upside down from biological trees. We typically draw the root at the top, and then it branches going down. The other biological terminology that we use is leaves. So if you are a vertex that has no outgoing edges, then you are a leaf in the tree. But in addition to using the biological terminology, we use terminology from lineage. So think of a family tree. And so if I were to pick some node, we'll pick this node here. In fact, we can color it to make it look different. So if I pick this node here, the node above it we refer to as its parent. The nodes directly below it we refer to as its children. All of the nodes, if there were multiple nodes going between here and the root, all the nodes on a direct path up would be called the ancestors, and everything that is below it is called the children. Okay, so we're kind of mixing our metaphors here. We have biological roots and leaves, but we also have parents and children. If you have two nodes that are the children of the same, then they are siblings. And you can kind of take that terminology as far as you might want when you're dealing with these. Other terms that you should be aware of are terms like the height of a tree or the depth of a node. So the depth of the node is how many edges you have to traverse to get from the root to that node. And you can tell I've switched from using the term vertex to node. I think I prefer saying it as well. So the root has a depth of 0. Everything at this level has a depth of 1. Everything at this level has a depth of 2. In this tree, this has a depth of 3. The height of a node is how far it is from that node to the deepest child. So this blue node here has a height of 2. Well, you only have to take one step down here to get to the leaf. Here you take 2, and of course the entire tree has a height of 3. We also use the term size. So the size of a node is equal to the number of descendants it has plus 1 for itself. So in other words, if you pick the size of a whole tree, the size is the number of nodes in the tree. So that's everything. When you pick a subtree, the size of the subtree is how many nodes are in that subtree, including the root of the subtree. So that introduces our basic terminology for trees, and we'll come back in the next video and we'll talk about how we could write some code that implements a tree.